And we are live. Perfect. Everything looks good. So this is a video where I will explore the idea of dividing by zero. This is me workshopping a grander video where I go in much more detail than I'll go in this video. So this is just random exploration of the idea of dividing by zero. So I'll start with why we cannot divide by zero, and then we will actually divide by zero. So let me quickly show you the notes that I made for this video. Wait. Let me share my screen. Also, I hope you guys are doing great. This video was actually requested to be by my close friend who is not a math student but who really gets interested in mathematical ideas when I talk to him. So I thought maybe why not show him a proof and exploration of why division by zero is generally prohibited. And obviously, in our exploration, we will go beyond those prohibitions and actually divide by zero. Let me quickly shift my camera out a bit. This should be better. Let's see. No, my head is cut. Okay, this is better. Okay, this you can see just some random scribbles on this paper. I was explaining this idea or exploring this idea with one of my peers at college, and he gave me really interesting insights in this process as well, which I will discuss later. But let me quickly show you a proof and then we go on from there. Before a proof, let's see what division actually is. So if you've divided a number with a number, I've divided a number with a number. So let's actually look at an example. So 4 divided by 2, we all know this is equal to 2. How do we know that? Because if I take a number 2 and multiply it by another number, which is 2, I get 4. Let's try 6 divided by 2. So what number when multiplied by 2 gives you 6 is reverse engineering division. So 3 times 2 is 6. Therefore 6 divided by 2 is 3. Pretty simple, pretty straightforward. You might have seen division as distributing something between a number of people. So let's say you have 6 things, you want to distribute them in 3 people. How many would each of them get? That's the basic idea of division, but we will try to have that idea, build upon that idea, and then make it abstract, and then see where we can go from there. So there will come a point where we will leave this physical sort of real description of division. We'll use that to make a definition that is much more abstract and then leave the original idea behind. This is almost like how we use numbers. So let's say if I say a random number like 7, you don't really think of 7 things in particular in your mind, but 7 is an abstract concept in your mind that lives there. So similarly, we'll try to see the pattern in division. We'll make that pattern abstract, and then we'll run from there on. Now we know what division is. If a number divides by a number, you need to make the bottom number equal to the top number, and whatever thing makes the bottom number equal the top number is your answer for your division. Now you might see a problem with division by 0. So 4 divided by 0, let's say it equals a number x. Whenever mathematicians use a letter, they use a letter for any number which they don't know yet. So people say that, hey, I lost interest in math when they started using letters instead of numbers. Well, those letters represent numbers, they just don't know what those numbers are at this moment. So we'll just call that number x for now. Then a little bit of algebra will tell you that you need to tell me a number x, which when multiplied by 0 gives me 4. Can we think of any such number which when multiplied by 0 gives us 4? Of course not. There does not exist a number which multiplied by 0 gives you 4. So that's why division by 0 is generally prohibited. But in math, we are allowed to make our own definitions, which is what we will do shortly. But before that, let me also tell you a common mistake that I see in some of my students that I tutor, is that if I do 4 divided by 0, They might also call this an error, a prohibition in division, or they might just say 4 divided by 0 is 0. Both of which are not true. This is just, let's just call this x as well. So 0 equals 4 times a number x. So what number that x might be, so that 4 times that number gives me 0, is just 0. So 0 divided by any number is 0 and perfectly legal in math. But a number divided by 0 is for now illegal. We'll make it legal though. Let's look at a proof, or a pseudo proof, I guess, to see why division by 0 is problematic. So let me write an equation. Let's say 4 plus 2 equals 2 plus 4. This is an equality. We know that addition is commutative, so I can write it either way. It's 6 on both sides. So let me do some algebraic manipulation on both ends. What I will do is I will subtract 2 from both sides, and I will subtract 4 from both sides. So you will get, let me maybe change colors. So what I will do is I'll subtract 2 from here, and I will subtract 2 from here as well, and I'll subtract from here and 4 from here. This will have me 4 minus 4. These 2's would cancel, plus 2 and minus 2, and I have 2 minus 2, which is still true. 4 minus 4 equals 2 minus 2. I've not done anything fishy just yet. Then I will factor out the 4. Factoring out the 4 basically means that you have a 4 outside and then you have 1s inside. So factoring basically means a number and then you have 2 numbers or more than 2 numbers inside. I'm going to call them B and C, and this would equal A times B minus A times C, which is a pretty common process, factoring out a number. If a number is common between 2 things that are added or subtracted, you can take out the number in multiplication. So 4 is taken out, and similarly I'll take 2 out as well, and I have 2 times 1 minus 1. Now if I have 2 numbers that are same on different sides of the equality, I can cancel those numbers out. So these simply just cancel out. 1 minus 1 and 1 minus 1 just cancel out. They are the same number, and I get 4 equals 2. So this feels like an absurd proof, and you might be able to see that I could have changed any of these numbers. Instead of 4 and 2, I could have literally chosen any numbers, and I could show that these numbers are equal to each other. And the problem is 1 minus 1 is 0 and 1 minus 1 is 0. So I did division by 0. And this is a particular kind of division that I did, which I would call 0 by 0 division, which is different from a number divided by 0. Both problematic as of now. So let's keep this proof in mind. I would call this a collapse, because all the numbers simply collapse to just one blob of numbers where everything is equal to everything else, or everything can be shown as being equal to anything else, and mathematics basically just becomes not useful if we allow this kind of division. So this is the 0 over 0 kind. Okay, let's actually go back to a number over 0 form. So I'm going to again choose a random number. Let's say 7 divided by 0, and let me think of a concept from maybe calculus. Some of you might be watching this thinking that a number divided by 0, okay, let's think about it. If I divide a number by a small number, I get a big number. For instance, if I divide 7 by, let me actually get my calculator as well, and let's do this calculation. So let's divide 7 by 2. So 7 divided by 2 gives me 3.5. Okay, let's divide it by a smaller number still. I'm going to divide this by 1. This would be 7. I'm going to divide this by even smaller numbers. So let's say 0.1. This would become 70. If I choose a smaller number still, 0.01, this would become 700. And the pattern starts to show up. The smaller the number on the denominator, the bigger the actual fraction that we get. So if we try to continue this pattern and maybe philosophically make it out there, if I'm dividing by smaller and smaller numbers, I'm getting bigger and bigger answers. What if I choose the smallest number, which again in this sense doesn't mean like a smaller number on the negative line, but the smaller number which is the closest to 0 or 0 perhaps, then I would get the biggest number as my answer. So when the denominator becomes smaller and smaller, the fraction becomes bigger and bigger. What happens when I choose the smallest, which is 0? I would get the biggest, which you might call infinity. So let's define this as equaling infinity. This again is a definition. I've not proven this. This is just a hunch that I have, an instinct you might say, and I'm just trusting my instinct, and again that instinct is built on some pattern that I see, but this is no proof by any means. But let's just call this infinity and see if anything else breaks, or does that fix division by 0. So there's still one more problem, or at least I would say two more problems. So we've introduced a new concept called infinity. Again, infinity is not a number. Infinity is just an entity, just like how 0 is an entity more than a number. So infinity is an entity that we have introduced, which appears when you divide a number by 0. Now there's one problem, or the first problem that would come up here is this problem. I think my camera is flipped, so let me just write this for you. So the problem here is that we have this number, we are dividing it by 0 and it equals infinity. What if I multiply both sides by -1? So multiply by -1 and multiplied by -1. This would make this -7 equals negative infinity. -7 over 0 equals negative infinity. And then I could just do 7 over -0 equals negative infinity. The negative sign in a fraction can freely move to either the denominator or the numerator. So I'm moving it to the denominator, and -0 basically is just 0. There is no negative or positive 0. So I can just remove the 0 on the denominator, and the problem that arises is that I have the same thing here, 7 divided by 0 equaling infinity and equaling negative infinity at the same time. So when I introduce the concept of infinity, I have an inconsistency. And you will see this whack-a-mole process go on from this point on. So it's not easy defining division by 0. So the first mole that we need to whack is I have this inconsistency. And if I have inconsistency, my math is not that useful. So I want to have a system that is consistent. So what might I do here? So let's draw a number line and see what results we have seen. So the 0 is in the middle. Infinity I'm going to put on one end and negative infinity on the other end. We've discovered that any number divided by 0 in this new definition of division by 0 with infinity shows that negative and positive infinity are basically the same thing. So let me just define them like this. Just joining the two ends. Whoops. So let's keep 0 in the middle. Positive numbers on the right and negatives on the left. But I've connected these ends. So they curl up, and they have connected to this point where there is only one infinity now. So in this model, or in this definition of division by 0, infinity is not negative or positive. It is just an entity called infinity. So I'll just leave it as infinity. In some notation, you might see infinity with a bar on top, just to be explicit. Does this solve all our problems? Not quite. Not quite. Before I move further, let me just give you, because we have introduced a new entity, infinity, let's see some properties of infinity. These properties might feel intuitively obvious to you, they might not. But some properties of infinity are that infinity plus any number, and again when I say any number, I could have just literally written x plus infinity, would just be infinity. So infinity is the biggest. Adding anything to the biggest doesn't make it any bigger, so it remains infinity. And then again, infinity minus any number, any finite number is still infinity. These are common properties of the regular infinity, which is seen in calculus and in some other fields of mathematics. Now what I will ask you is, what would be, let's say, 0 times infinity? 0 is the smallest, infinity is the biggest. What happens when I multiply both of them? If you are more comfortable with multiplication by 0, you might say that, hey, 0 times any number should be 0, so this should be 0. But if you're more comfortable with the fact that infinity times any number is also infinity, so this is still a question mark. This is still a question mark. We don't know what is 0 divided by infinity. And perhaps a much more clickbaity question here is, what would be 0 divided by infinity? Or infinity divided by 0? Well, what would be 0 divided by 0, which was the other inconsistency that we have not whack-a-moled yet? So these are still inconsistencies that we have not dealt with, and these inconsistencies are also called the indeterminate forms if you have done calculus. So for the calculus students, they don't like these kinds of infinities and these kinds of indiscriminate forms because they make their limits difficult to calculate. Because again, in limits we have the concept of infinity, and it is a concept that is based on this process or this pattern following. What now then? So we have this, we introduced this infinity, we seem to have broken more than we have fixed, but what can we do from this point on? Let me try to make this consistent by introducing one more entity. And again, you might think that adding more entities seems to break more than it meant, but I would say that this entity, it balances things out quite nicely. So I'm going to introduce 3 things here. So any number divided by 0 is how I will define infinity. Any positive number divided by 0 is how I will define infinity. And x cannot be 0 itself. X can be any number, positive, negative, or whatever, cannot be 0. So any finite number divided by 0, and the number cannot be 0 itself, would be infinity. That's my definition of infinity. And for 0 divided by 0, I'm going to introduce a new concept or a new entity. I'm going to call this entity nullity. So we have 0, we have infinity, and we have nullity. So 0 divided by 0 is nullity, and I am going to claim that this solves at least 99% of our problems. And again, I have not told you any properties of infinities, and I'll not tell you any properties of nullity as well. As long as you remember this definition, this is how I will define both of these, and I'll start to play with these numbers and you'll see how they work. So let me actually get some of my let's actually see a couple more examples here. So let's do, oh, there's another problem which is also like infinity minus infinity is also a problem. I'm subtracting infinity from itself, but again, infinity is not a number that can be subtracted as such. This cannot really be equal to 0, because if this is equal to 0, that also leads to some problem. Then again, we had this problem, 0 times infinity, which again, if I have, let's say, any number divided by 0 equals infinity, I have 5 equals 0 times infinity, and then I could replace this 5 with any number, and that would equal 0 times infinity. So again, I can show any number equal to any other number. That would be another collapse. Then I have this Yeah, I think that should be fine. So I have these two definitions now. I have x, any number divided by 0, infinity, and 0 divided by 0 as the definition of nullity. Now let's try to fix or try to get rid of these indeterminate forms. Let's try with 0 times infinity. And then on the other side, we'll try 0 divided by infinity. Let's see what this is. So this I will do as 0 times infinity is x divided by 0. That's my definition of infinity. So instead of writing the symbol infinity, I'll just write x divided by 0. And then I'll just solve it out and I get 0 over 0, which is my definition of nullity. So this fixes some things. 0 times infinity is nullity. Great. Let's try 0 divided by infinity, which is just 0 times 0 over x, which is just 0 over x, which is, oh, this is actually not even a problem. I made the same mistake that I tell my students not to make, which is just any number divided by, or 0 divided by any number is just 0. So 0 divided by infinity is not a problem. 0 divided by x is just 0. So we have verified that this is still true in our system. We've now found out that 0 times infinity is actually nullity. It's neither 0 nor infinity, is this third term that we have introduced. Let's try infinity divided by 0. So any number divided by 0 was a problem. What about infinity divided by 0? This again, I'll write infinity as x over 0. And this divided by 0 equals x over 0 times 1 over 0. So in division, we just take the reciprocal of the fraction and that's it. So this is just x over 0, which is still just infinity. So that checks out. We have a consistent answer. We don't have any two answers for the same thing, inconsistencies. So we have infinity divided by 0, which is still infinity. What about other indiscriminate forms, like let's do infinity minus infinity. So infinity is just x over 0, any number over 0, minus x over 0. If you know fractional subtraction, all you do is just multiply the denominators. So 0 times 0 is just 0. And then cross multiply them. So 0 times x and then 0 times x, which is just 0 minus 0. So I have 0 minus 0 over 0, which is just 0 over 0, which is nullity. So infinity minus infinity is neither infinity nor 0 again. It is the third entity that we introduced, nullity. So I've done infinity minus infinity. Actually, curiously enough, this is not an indiscriminate form in calculus. Infinity plus infinity in calculus would just be infinity, which I don't quite like. But in this system, infinity plus infinity, by the same or by a similar process as shown above, is also nullity. Great. Now we have introduced this new nullity symbol or this nullity entity. What if we divide something by nullity, or divide 0 by nullity, or nullity by 0, and see how nullity behaves with 0 and infinity? Maybe that will break some things. So let's try maybe 0 over nullity, which again, 0 divided by any number should just be 0. So let's see if this is still 0 or not. So this would just be, actually this would not be 0. So this is 0 divided by 0 over 0, which would be 0 times 0 over 0, which is just 0 over 0, which is nullity. So 0 divided by any number is 0, but 0 divided by nullity, it's telling us it should be nullity. And I think that by the same logic, nullity divided by 0 would also be nullity, but let's check it still. 0 divided by 0 divided by 0, which is just 0 over 0 times 1 over 0, which is again just 0 over 0, which is nullity. Let's maybe try nullity divided by infinity. Maybe that will be something curious. So this would be 0 over 0 divided by infinity, which is 0 over 0, divided by x over 0, which is 0 over 0 times 0 over x, which is again just 0 over 0, which is nullity. So this is still consistent. Now let's see. Now let's quickly summarize the properties that we have. Okay, so we have 0 divided by infinity, which was nullity. We have 0 times infinity, which is again nullity. We have infinity divided by infinity, which we did not do. Maybe we should do that real quick, which is x over 0 divided by x over 0, which is x over 0 times 0 over x, which is just 0 over 0, which is also nullity. So infinity divided by infinity is also nullity as well. And 0 divided by 0 is nullity still. Then there are properties of nullity as well. So let's try adding a positive number to nullity. Any positive number or any number, any non-zero number to nullity. Let's see how nullity behaves with normal numbers. So nullity is again 0 over 0. So I do 0 over 0 plus x, or I could just say x over 1, which would just be 0 on the denominator, and then 0 plus 0, which again is just 0 over 0, and nullity. So nullity plus any number is also nullity. Nullity minus any number would also be nullity. Nullity times any number, I hope you can see this, nullity times any number would just still be 0 over 0, which is nullity still. So this is nullity as well. And then nullity divided by any number, and any number divided by nullity would also be nullity. Great. And this is nullity still. So we have three things here. We have, this is how I will now define all of my entities that I've introduced. So I have any number that is non-zero divided by 0 equals infinity, 0 over 0 equaling nullity, and basically any number that is non-zero and that is not nullity itself would be 0 basically. So this solves most of our problems. This is actually very much consistent with a lot of arithmetics. And this to me feels like a really beautiful and elegant idea. I would always philosophically think of 0 as being a really beautiful concept. Then when I got introduced to infinity, that seemed like it had a really close link with 0, and it felt almost poetic that the smallest and the biggest are so closely linked with each other. But again, when I saw this trinity here with nullity balancing the two, that felt even more powerful and again philosophical in a sense that these three make a consistent triangle of sorts that helps prop up the math. And again, in this system, division by 0 is completely legal. Now, do we lose anything here? Now, numbers or normal arithmetic has many core concepts and many core principles which we call axioms. So axioms are truths about a system that are not proven but that are accepted as true. So you and me, if we are building mathematics, and if it is a mathematics based on axioms, what we will do is you and I would agree on some rules of mathematics, and we'll try to make those rules simple, and we'll try not to have too many of those rules. So we have those rules, and then anything we build off that math would use those rules forward. So I will use maybe rule 1 and 2, which we would have agreed on, and make a theorem. Then I would use that theorem to prove another theorem, and this is how mathematics gets built upon itself. So if you were really a student of math, you would start at the real bottom where we have these truths about mathematics. And for just normal numbers, we have about, I think, 13 or so axioms. And some of those axioms are basically that uh, a number times 1 is always itself. We call that the identity axiom. Or an axiom could be that if you have x plus a number and you have a number plus x, so if you flip those around, you still get the same answer. So 4 plus 2 is equals 2 plus 4 is not something that we prove, but is an axiom that we accept as true, which again, it is built from instinct, just like how I built a number divided by 0 equaling infinity from an instinctual pattern that I saw in division. So similarly, we have this concept. We also have uh, transitivity, which is basically if a number equals a number and the second number equals a third number, then the first number equals the third number as well, which again might seem obvious, and these axioms, most of them are really obvious, but this is the core of a lot of mathematics. This is the building blocks of mathematics. This is called transitivity, and this we actually lose if we only introduce infinity. But with nullity, transitivity is preserved. And again, if transitivity is not there, your mathematics becomes really uh, incompetent at doing anything. And again, this is not for application's sake, but really it's just boring math if you don't have transitivity. Then the axiom that we actually we lose, I think, 2 to 3 axioms. But the really important axiom is the distributive axiom. So let me actually bring out my notes, my rough notes. And again, the distributive law, just for just for the sake of mentioning it here, if you have a number a and you multiply that number with b plus c in bracket, in parentheses, this equals a times b plus a times c. So this is called the distributive law because a gets distributed to both b and c. This again is not something that we prove. This, if you see in real life, this is how numbers behave. But again, it is accepted as true as one of the axioms. But in this mathematics, this axiom does not hold. It holds for all the positive or negative numbers that you would use. It would still hold for 0 as well. But it would fail for some examples. Let me actually quickly find such an example and see if it holds. So let's say that a equals I'm going to say that a equals infinity, b equals 1, and c equals 1. So these numbers or these entities are all part of my system. So what I will do is I will do infinity times 1 plus 1. Wait. Let me think. Yeah. And then I will do infinity times 1 plus infinity times 1. So on the left hand side, I'm using this form of the distributive law, and on the right side, I'm using this form. And they should both be the same, otherwise the distributive law does not hold for all numbers. It might hold for most numbers, and in fact it does hold for 99% of the numbers if I were to just throw out a percentage out there. But it does not hold, or I claim that it does not hold for this number. So infinity, again, I'm not going to use it as the symbol infinity because we have defined infinity as a finite number divided by 0. So I'm going to say this x over 0 times 1 plus 1 is 2. So this equals 2x over 0, which again is just 2x is just a finite number still, which would just be infinity. So on the left hand side we have infinity. Let's see what do we get on the right hand side. Well, infinity times a number, and again I'll change infinity to 0, x over 0 times 1 plus x over 0 times 1, which again would just be x over 0 plus x over 0, which would be infinity plus infinity, which again, uh, in calculus, infinity plus infinity would just be infinity. But we've just proved here that, did we? Yeah, we just showed that infinity plus infinity is nullity. So we have infinity equaling nullity, which is obviously not true. So the distributive law does not hold for all numbers. And this is where all the information that I wanted to give you stops, and this is where actual exploration goes on. So this information is not mine. I've looked at some YouTube videos, some research papers on this concept, and I've basically compiled all the information and tried to just work through communicating that information and just absorbing the core concept of it all. But this is where the actual exploration of the matter shows up. How would I actually now explore these concepts into realms that have not defined it yet? So now I have these axioms, I have these definitions of infinity and zero, and I'll borrow all the axioms from normal numbers as well and see what breaks and what does not. Where are my limits of this kind of mathematics? There's a reason this kind of mathematics is not popular and it's not used commonly, and it's almost demonized in a way that, hey, don't divide by zero. You can divide by zero, it's not prohibited, as long as you are ready to face the consequences. So let's face the consequences. And those consequences is what we call, or what would be at least one form of research in mathematics. It's just basic exploration. So in basic exploration, I also want to try the distributive law works with negative signs as well. So I want to try b minus c and ab minus ac. Let's see if that works or not. And I'll keep a equals infinity, b equals 1, and c equal 1 still. Great. So I have infinity times 1 minus 1 equals infinity times 1 minus infinity times 1. Great. Infinity times 1 minus 1 would just be infinity times 0, which we've already proved is nullity. And surprisingly, infinity times 1 is just infinity times 1 is just infinity minus infinity is nullity still. So the distributive law holds if I have a negative sign there. And honestly, I explored many examples here. So I've explored 1, 2, 3, 4, 5, 6, 7, 8, almost 10 examples here. And only for one of those examples did the distributive law not work. And obviously, if you're not using zero nullity, or if you're not using infinity and nullity, all of the examples would work, because that's just normal numbers without infinity and nullity. But even with the introduction of infinity and nullity, there are only just a few cases that do not work. And not today, but I think I should explore why there are not a lot of instances where this breaks. Because whenever there is something in mathematics, what happens is that sometimes you have many answers, sometimes you have no answers. And in both of those cases, it's really boring. If you have nothing, there's nothing to explore. If you have infinitely many things, there's really nothing to explore as well. But whenever there is only finite ways you can break something, those finite ways needs to be explored. So again, not today, but I do want to explore, just like whenever I have time, I'll have my notebook out and just try to find more and more examples where distributive law breaks. Now obviously here, I could have replaced this with any finite number, and this would have broken. I would call this one category of solutions that would break the distributive law. I want to see if there is any other category, and if there is not, then why is there this one category, and does it relate to anything else, and where exactly does the distributive law break? Also, a quick side note, if you have 0 times x equals let's say y equals x times 0, what do I want to say? Yeah, let's say this. In normal algebra, you would just say that y equals 0. So we lose this property of algebra as well, because if if x is infinity or nullity, then y is not necessarily 0, it would be nullity. So quirks like this, you would need to keep in mind. But again, these are not inconsistencies. These are just newer ways of doing things. Now to the exploration that I did with one of my friends at uni when I showed all of these proofs to him. So let me show you what the rough version of this would look like. So I also showed him the 4 equals to 2 proof, which he quickly pointed out that I did division by 0. But again, it's not about trying to fool you into thinking two numbers are equal, but to do the opposite, where you would now realize why division by 0 breaks things. And again, I would like to call this like collapse of numbers, where every number equals any other number. So mathematics becomes a lot incompetent. Then again, I showed him nullity. I showed him this. This is actually called this is called circle algebra, because it is circular and it is or is it algebra or circular arithmetic? I think it might be it's actually circular algebra, I think. And then if they put nullity here, and then you have these spokes for some reason, I don't quite remember, but this is called wheel algebra. So this is a normal or a common field of mathematics called wheel algebra, where division by 0 is consistent. Then again, I showed him all the fringe cases, all the indeterminate forms. We see that they are consistent here. In nullity plus 1, nullity, nullity times infinity, nullity, nullity times 0, nullity, nullity divided by infinity is still nullity. And then I draw this triangle, almost mythical triangle there. I tell him about wheel algebra. I also tell him that in 99% of the cases the distributive law holds, but in one case that I had here, it does not. He didn't question me, he just accepted that, yeah, it does not work. This is where we started to explore things that are not defined per se, or that are not easily, you cannot extrapolate easily from these basic definitions, how exponents, for instance, might work. So this is where the exploration began. We had infinity raised to the power of 0. So this is also an indiscriminate form in calculus. I don't quite remember how we solve or get rid of this indiscriminate form, but this also is an indiscriminate form. But now that we have a definition of infinity, which in calculus we don't have such a definition of infinity, what I will do is I will just do this. So infinity is just any number divided by 0, so I replace infinity by my definition of infinity, and raised to the power of 0 is just x to the 0 over 0, which is just x to the 0, so any number raised to the power of 0 is just 1 divided by 0. 1 is just a number, and 0 is again infinity. Any number divided by 0 is infinity. So infinity raised to the power of 0, our system says that it should be infinity. And again, just to recall, by definition, any number raised to the power of 0 in normal mathematics or in conventional mathematics would be 1, just like how I've done here. So this is by definition I've done this. So as a definition of exponents, we say that any number raised to the power of 0 would be 1, but infinity raised to the power of 0 is actually not 1, not 0, not nullity, which I expected actually. I was like, whenever there is interaction between 0 and infinity, I've only seen nullity, so maybe it would be nullity, but in this case it is infinity. Let's try the opposite as well. Let's try 0 raised to the power of infinity, just for exploration's sake. And this would be 0 to the power of x over 0. Now this is fractional exponents, and fractional exponents, you might think that you have not seen them or you don't know how to work with them, but you've actually worked with fractional exponents if you have worked with square roots. So the square root is actually a fractional exponent. This is converse of the square function. So if the square multiplies the number by itself, this sort of reverses that multiplication, and it is also written as 1/2, or the fractional power of 1 over 2. So 0 square root is 1 over 2, and I write this in this way because I want to do the reverse math of this as well. So let me quickly show you some examples. Let's say you have 5 raised to the power of 3 halves. So this you would write as square root of 5 cube. Let's do another fractional power. Let's do 5 to the 7 third. This you would write as cube root of 5 to the 7. So this 3, it goes here, and there's an invisible 2 here as well, and this 7 goes here. One more just for clarity's sake, let's do 11 raised to the power of 19 over 21. So it would be the 21st root of 11 to the 19. This is how fractional powers work. Again, we are not dealing with numbers per se, but we are dealing with arbitrary quantities here. So this becomes the 0th root of 0 to the x. And now x is a finite number. 0 raised to the power of any finite number. Again, exponentiation basically means that you take the number, you take the degree or the power on top, and you multiply that number that many times. So 2 raised to the power of 4 would be 2 times 2 times 2 times 2. So 0 raised to the power of x, and x can be any number, is just 0 times 0 times 0 times 0, which I think we all know would just be 0. Now what I have here is a problem still. Now I know how to do square root of 0 with the square root function. Let's do square root of 4 and see how the square root function works. So the square root of 4 or the square root function basically asks you to find two numbers that needs to be the same, which when multiplied give you the number inside. So because there is a 2 here, I need two such numbers which when multiplied give me 4. So the two numbers would be 2 and 2, and therefore the square root of 4 is 2. Again, for the square root function, because there is a 2 here, I need a 2. Let's say I have a cube root function, and let's say I'm finding the cube root of 8. I need to find three numbers which when multiplied to each other give me 8. You might have a guess, it is 2 times 2 times 2. That's why the cube root of 8 is 2. So the square root of 0, or the 0th root of 0, basically asks me to find it is asking me to find a number. No, my brain is breaking. So I don't, if square root asks you to find two numbers, cube root asks you to find three numbers, 0th roots is asking you to find 0 number, which when multiplied give you 0. And that is something that I don't know if we can figure it out. My instinct says that this should just be 0. So in 0 raised to the power of infinity, my instinct says it's 0, but my instinct here would say that this would be, I don't know, nullity, but my instinct is not always right. So this is a problem still. My math didn't give me like an exact answer out. I have this 0th root problem, and I don't know how to define consistently the 0th root of a number. If 0th root of 0 is just 0, would the what would the 0th root of 5 be? That is still a problem. And again, the 0th root of 5 would just be 5 raised to the power of 1 over 0, which would just be 5 raised to the power of infinity. And again, my instinct says that any number multiplied by itself infinitely many times should give you infinity. So again, my instinct says that this should be infinity, but I don't know if that instinct would hold any water. This is math exploration. Now I am out of my comfort zone. Now I am in the exploration territory. So let's try to explore this. Let's see where this goes. Okay. So any number raised to the power of infinity is still a problem in our system. There are some more examples that did actually give out an answer, and maybe I can use those examples to build a stronger foundation for myself. Again, another problem that him and I were exploring was the problem of -1 raised to the power of infinity, which would be -1 times -1 times -1 times -1 times -1 infinitely many times. Now this, if I have -1 raised to the power of any odd power, let's say 2, this would just be -1 times -1, and these negatives would cancel to give me 1. If I have -1 raised to the power of an even power, I would get 3 negatives, which would be a negative. So in in even powers of -1, I get just 1, and in odd powers of -1, I get -1. So it alternates between -1 and 1 depending on the power. And with infinity, I don't know if infinity is even or odd. The concept of even and odd for 0, infinity, and nullity does not exist, which is, again, might seem like a problem, but again, for 0, we don't really seem to have a problem that 0 is neither even nor odd, or both even or both odd, or sometimes 0 is considered even actually. But again, for nullity and infinity, they don't have such properties still. So again, this is where we might need to add more axioms, add more definitions, which makes the math maybe a bit more clunky, but there's no other way out. We might need to, again, those definitions must come from instinct, or if they don't come from instinct and you just add them without any reason, you need to explore the math further out to see if any inconsistencies show up. This is actually one way that we prove things. So if I need to prove a thing, and I don't know how to prove it directly, a direct proof would be a proof from the axioms. So let's say I have this statement out there, and I don't know if that statement is true or not. I could take the direct route, which would be to build from axioms or known theorems to then get to the result. But another way I could find the proof is called proof by contradiction, which is a really fascinating idea. And in that, what I will do is I will assume the opposite of that statement. This is a common way we prove that square root of 2 is irrational. So we would assume that square root of 2 is rational. So assuming the opposite, and then just exploring the math and finding at least one contradiction. And as soon as you have a contradiction, as soon as you have a inconsistency, you can say that the opposite is not true. So if it is not rational, we assumed it to be rational, we found an inconsistency, so it must be irrational. And this can only be done with things that can either be one thing or the other. It can either be even or odd. So let's say I'm trying to prove something is even. I might I might assume that it is odd and then find an inconsistency. This would be what we'd call a proof by contradiction. So basically what I'm doing is, in my system of mathematics, I'm turning a knob the other way and seeing if anything breaks. If it breaks, then I know that the knob needs to be that way, and that is enough of a proof. That is as good a proof as it can be. Again, I'm not going from 0 to that point. All I'm doing is just changing the point and seeing if anything breaks. And when I say anything, it could be anything really that we've already proved somewhere else. And again, I think it's a good proof to see. A proof by contradiction, though can be really difficult, are some of my favorite proofs. Okay, so this was still a problem. So I'm going to mark this problem as well. I'll try to do some exploration before I make the final video of this. This is just me workshopping and trying to find my flow of things and trying to explain things. And as I explain, just learning stuff myself as well. Then I have so we had what other inconsistencies did we find? So we defined 1 over infinity to be 1, or we defined x over infinity Wait, did we do 0 to the power of infinity already? We did. Oh no, we tried 0 to the infinity and it did not work. Okay. So x raised to the power of infinity, and remember x here has three possibilities, or it can be any number, and number I'll just write pound. X can be 0, x can be infinity, and x can be nullity. Let's be consistent, let's be organized with it, and let's try all of these options. And again, if I don't get an answer from my method, all I can do is just make an educated guess and make it one of my assumed theorems or assumed axioms and see if I can find anything that breaks. So let's try with a number, and let's try with 1. So 1 raised to the power of infinity. My instinct says that this should be 1. 1 times 1 times 1 times 1. Again, it is my instinct. This is not a proof, but it feels like a strong enough instinct that I believe this should be true. So let me just conjecture this. Let me just say that 1 raised to the power of infinity is 1. So x raised to the power of infinity equals 1 when x is 1. Let's try another possibility. Let's now try x equals 0 raised to the power of infinity. 0 to the infinity we tried before. It did not work, or this feels like, at least my instinct says that 0 times 0, no matter how many times we do that, it should be 0. So I'm going to define this, at least for now, as 0. But let me just do this exploration here further to show you how this would work. So infinity, I'll go x over 0. Then I have 0 to the x and the 0th root of 0. And the 0th root of 0 I'm saying is 0. But again, if I'm defining, when I say 0 raised to the power of infinity is equal to 0, the consequence of that is that the 0th root of 0 is also 0. Now I need to define 0th root of some other number. Should that also be 0? What's my instinct there? And would my instinct be consistent with the instinct above it? The 0th root of x would be, let's try, so this would link back to this, and I hope I can show this to you. Now x is any finite positive number. I should have mentioned this. So for a number there are two options still. It could be positive or negative, and in this case let's say x is a positive number. So x is a positive number raised to the power of infinity, and x, I should mention here that x is greater than 1, and this matters as well. So any number greater than 1, let's say 1.1 or something, if you multiply 1.1 enough times you would get bigger and bigger numbers, and if you're multiplying it infinitely many times you should get infinity. So x over infinity, my instinct says it would be infinity if x is positive and greater than 1. So this is infinity if x is greater than 1. Okay, what if x is less than 1? Let's try that possibility as well. If x is less than 1 but greater than 0, let's try that. So x is between 0 and 1. In that case, what would happen is we would get a fractional number. So I would get, between 0 and 1 could be 0.5 for instance. So 0.5 raised to the power of infinity. If you multiply 0.5 enough times, and I'll show you some of those calculations. So 0.5 times 0.5 equals 0.25. So this number is smaller than the number we begin with. Let's multiply this by 0.5 again, and the number continues getting smaller and smaller. I'm going to multiply this again and again and again and again. So the number becomes just after many multiplications, it becomes this. So it gets closer and closer to 0. So if a number is between 0 and 1 and you multiply it infinitely many times, I'm going to say that this also becomes 0. So 0 to the infinity, my instinct said, should be 0. The consequence of that instinct is highlighted here. 0 to the infinity, the 0th or any positive number raised to the power of infinity, my instinct says should be infinity. And the consequence of that is that the 0th root of any number would then also be, by that definition, infinity. So this and this, if I assume this to be true, then I must face the consequence of saying that any positive number or any number greater than 1, the 0th root of that number would be infinity. And 0th root of any number that is fractional, so between 0 and 1, would be 0 still. Again, a bit clunky, but this is what exploration looks like. Now let's try 0 or infinity raised to the power of infinity. I don't know this. I don't think I've explored this. So infinity by definition is x over 0. Raised to the power of infinity is again x over 0. And again, x over 0 I can write as the 0th root of x over 0 raised to the power of x, which would just be 0 raised to the power of, or 0th root of x to the x of 0, which would be 0th root of x to the x is still just a positive number, so I'm just going to call this y. It's not the same number as x, but it's still a positive number. It's not infinity, it's not nullity, and it's not 0. Divided by 0 would be this. This becomes infinity. So any positive number or any finite number divided by 0 is infinity, and I am back to the same thing, which is infinity to the 1 over 0, which is again infinity over infinity. So it did not give me any answer, at least with this process. So I need to find an answer for this as well. So positive numbers worked. Numbers 0 instinctively still works. Infinity over infinity raised to the power of infinity did not give me a consistent answer. Let's try nullity, which at first seems scary, but let's see what that is. So nullity to the infinity would be 0 over 0 raised to the power of x over 0, which would just be 0 over 0, and the 0th root of x, which would just be 0th root of 0 over 0, which would just be 0th root of nullity, which is a problem. Still, I don't know the 0th root of nullity. It is hard to define that as well. Any other number that we want to explore? There were some other explorations that did end up working. Okay, there is a piece of intuition that is not mine, but I think which is interesting is this. If we have 0 raised to the power of, and again you can see here how this exploration, x raised to the power of y, where x can be any number including 0, infinity and nullity, y can be any number including 0, infinity and nullity, leaves you with many options of exploration. And this is just one area of mathematics we are exploring with our new entities, infinity and nullity. So he had this intuition: if we have 0 raised, or if you have 4 raised to the power of 2, this would be 16. If you have 4 raised to the power of 1, this would be 4. If you have 4 raised to the power of 0, this would be 1. So all that is happening is that 16 divided by 4 is 4. 4 divided by 4 is 1. Let's see some more examples. Let's say 3 cube is 27. 3 squared is 9. 3 raised to the power of 1 is just 3. 3 raised to the power of 0 is just 1. And again, this is division by this, division by 3, division by 3, and division by 3. So similarly, he proposed that if we have 0 raised to the power of 2, it should be 0. 0 raised to the power 1 should be 0. 0 raised to the power of 0. He said that this should be 0. Wait. No, his intuition is a bit off. So this divided by this would become 0 over 0. So his intuition was to say that 0 raised to the power of 0 is, which again is an indeterminate form, should be nullity. And again, this we are going off in a different direction, trying to explore this. I don't have the root function here, the roots of anything. But this would also assume that if we go from any power of 0 to any power 1 less than that, this would be nullity. This would just say that 0 raised to the power of any number would be nullity, which again is a consequence. Either I need to define something better than this, or I need to accept this consequence that 0 raised to the power of any number here would be just nullity, which also makes things, it might make things more consistent, because so much of inconsistency would just be solved with this one number nullity. But it's also not that useful. Just having this one number put over all your mistakes or all your inconsistencies, your problems, does not really fix them. It only just hides them. What other numbers can we explore? Let's try, did we try nullity raised to the power of nullity? I think it would have the same problem. Let's try nullity raised to the power of nullity. This would just be 0 over 0 raised to the power of 0 over 0, which would just be the 0th root of nullity. No. Yeah, this would be the 0th root of nullity. The 0th root of nullity. So interestingly, nullity raised to the power of infinity is equal to nullity raised to the power of nullity, even though I don't know what these answers are. This is interesting. This might be a point of leverage where I can now see other things that equal each other and see if they make sense. What other results I had? I have this result here. Infinity to the infinity equals 0. Let's try infinity to the nullity. So infinity is any number over 0. Nullity is 0 over 0. This becomes x to the 0 over 0 to the 0. Actually, this is made a mistake here. No. So this is the 0th root of x to the 0 over 0 to the 0, which would be the 0th root of in 0th root of 1 over 0 to the 0, which again 0 to the 0 might instinctively seem like it's just equal 0. That's what I accidentally did here, but 0 to the 0 is still not defined. We have not yet figured out what is 0 raised to the power of 0. And again, this isn't a problem just with my math. It is still undefined in just regular old math, because this is not using infinity or nullity, this is just using 0. So 0 raised to the power of 0 is not defined in normal math, but I was hoping that with my new entities it would be magically defined. If not magically, let me see if I can brute force my way through it. So we have two instincts here. One of the instincts is that 0 raised to the power of anything should just be 0. Another instinct is that this division instinct, so when you decrease the power, the number gets divided by itself, is that 0 to the 0 might be nullity. If I say that 0 over 0 is just 0, then I would get infinity here. If I say 0 over 0 is nullity, then nullity divided by any number would just be, let's quickly see, so 1 over nullity would be 1 divided by 0 over 0, which would just be 0 over 0, which would just be nullity. So it's either this or 0 to the nullity. If we assume 0 to the 0 to be 0, then we get 0 and square root of infinity. Otherwise we would get 0 and square root of nullity. And 0 square root of infinity we've seen before as well. Where did it go? So 0 to the, so if we assume this, then we would also need to say that this infinity raised to the power of nullity is the same as infinity raised to the power of infinity. Again, I don't know what that is, but they are the same, which again is interesting. Again, that is only true if I assume this. Otherwise it would be, so let me scratch this result as well. Let's do this again. So this would be 0 to the 0 over 0 to the 0 and the 0th root of this, which would be the 0th root of 0 to the 0 can either be 0 or it can be nullity. But if we assume 0 to the 0 to be 0, I would get 0 over 0 here. If I assume 0 over 0 to be nullity from this instinct, I would get 0 to the nullity over nullity. But nullity divided by nullity, so this becomes 0 to the nullity, and this is nullity over nullity, which we have not explored yet, but I think nullity over nullity would just be, oops, so this becomes 0 to the nullity, and nullity divided by nullity, my instinct, or not my instinct, but in my head I can see that this would be 0 over 0, which is just nullity. So no matter what definition of 0 to the 0 I take, even if I take 0 to the 0 to be 0 or 0 to the 0 to be nullity, I get the same answer here, 0 to the nullity, which is the same here. So this is still true. This instinct is still true and important. So nullity raised to the power of nullity is the same as nullity raised to the power of infinity, regardless of how we define 0 raised to the power of 0. So let me just box this for myself. And what other combination have we missed yet? Yeah, this might be an anchor here. Yeah, I don't know though. This feels like a question we should be able to answer. 0 raised to the power of 0. What other? Let's try nullity raised to the power of 0. This would just be nullity, right? This would just be 0 over 0 raised to the power of 0, which would either be 0 to the 0 over 0 to the 0 if defined as zeros, it would be 0 over 0 nullity. If defined as nullity, it would be nullity over nullity, also nullity. So no matter what, infinite nullity raised to the power of 0 would be nullity. This is regardless of how we define 0 raised to the power of 0. What else? Let's do 0 to the nullity. This would be 0 to the 0 over 0, which would just be the 0th root of 0 to the 0, which again, now we have two options here. It would either be 0 to the, if we define 0 to the 0 to be just 0, or 0 to the 0 to be nullity. And if we define this like that, then this 0 to the nullity would equal this result, which is nullity over nullity raised to the power of nullity and nullity raised to the power of infinity. So nullity to the nullity and nullity to the infinity. Which would equal 0 the root of nullity. And if we define this as 0 to the 0, then it would just be 0. Or if we define the 0th root of 0 as 0 as well, which we have done here. But again, this is still an assumption. I don't know, I think that is it for today. I'm really spent, and I think the next time I'll meet you, I'll probably have some more exploration done with this. But this is a gist of how I would explore math whenever I get a concept. Again, playing with axioms is one of the most fun thing that I like to do in math. All you do is just look up all the axioms for any math that you feel comfortable with, and just try to break some axioms and see what are the consequences of breaking axioms, or maybe tweaking them, or maybe removing them altogether. So one of the axioms in I think one of the axioms of numbers is that multiplication by 0 is equal to 0. So what if you remove that axiom? What are the consequences of that? What if you remove transitivity? What are the consequences of that? Or what if you remove the distributive law? And seeing the consequences of that play out is a really creative and fun way to explore math. So this is it for today. Let me quickly stop this screen share and off. Perfect. So 1 hour and 20 minutes of math exploration. And again, look forward to a video that I will be posting about all of this stuff once I have sort of a conclusion out of this, seeing the boundaries where they lead, maybe trying to break through the boundaries and seeing if we can get something more consistent, and maybe being able to answer questions like 0 raised to the power of 0, which again in normal math is not defined, but maybe with this introduction of new entities, which again is consistent with just normal arithmetics, but does break with exponentiation. And maybe next time we might explore it with other ways where we might use this in calculus and see how this breaks calculus, or maybe helps us explore calculus and stuff like that. So anyways, that is it for today, and I'll see you next time.